And for this next example, let's call that example 4. Okay. So we want to find all local maxima, all local minima. Okay. And then now function here minus 1/2 x to the 4th plus x cubed. So it's minus 1/2 x to the 4th plus x cubed. So the function we have here, as usual, actually allow me to add in one more information, one more extra detail right here, but it's important. We want to find all local maxima and all local minima and the absolute value, the absolute maximum and the absolute minimum, right? Inside, for that function, inside of the interval from -7 to 7. Okay. So now let me quickly put in a graph right here for you to understand. So this is our minus 1/2 x to the 4th plus x cubed, like that, right? And it goes like that. And then we want to, the problem wants to restrict the function down to only anywhere from -7, okay, to 7. And so the graph looks like this. All right. So in that scale right here, you can see, yeah, our function. It's looking like that. So it's not the whole complete graph right here, but and so now because the scale is no longer a square scale, so it looks a little hard to recognize right here, but you can see that the function is hitting up a little bit with a peak here, with a high peak up here. Okay. If I zoom that in a little bit, right, and you can see that it's slightly hitting up. And so if I put that back in square scale right here, then you can see that more clearly. See, the function actually hits up a little bit, right, and hits down, and then we restrict that down in between -7 and 7. Okay. And so let's tackle it down. So be aware that there's an interval of restriction for this problem right here, but for now we don't need to worry too much about that. I showed the graphical illustration that instead of taking the complete function, right, we only want to restrict the function for x values anywhere from -7 to 7. But that's it. And then for now, we don't need to. Let's hold on to that worry about the interval. Let's just do the usual work, because in the end we have to find local maxima and local minima, and then at the end find absolute maximum and absolute minimum. I will explain what it means as we go on, as we go through the problem. And right now those are new terms, so that's why I'm indicating them with the red ink. Okay, so go ahead and find the critical values. So now for our critical values, right? As far as the critical values, I'm gonna have to find. So f prime here comes out -1, -2 x cubed, right, plus 3x squared. And see, for a problem like this, then it's best that we can factor, and it's always good that we can factor our derivative, because the work here later on when we do the sign chart and the sign check and all of that, and it's gonna heavily depends on the factor product like that. So I'm gonna factor out the x squared, okay, and here I'm looking at -2x plus 3. So that's our derivative in factor form like that. Okay, so now we're gonna, and once again the argument here is that f prime is, and the problem is gonna get lengthy, so I'm just gonna say it verbally but without writing that down here. But f prime is a polynomial. So once again it's defined everywhere, so we don't need to worry in order to find the critical values right here. We already ruled down that possibility about having any x value making it undefined. So now we only need to simply set f prime of x, right, to equal 0. So that all we worry about now is that we're going to look for those x values making f prime equal 0. And that now leads to, right, we're going to have an equation to solve for. So we're looking at x squared, okay, times -2x plus 3 equals 0. And then I directly use that factor form right here instead of beating around the bush, because like I said, I'm very limited in board space here. And so basically we set the derivative equals 0, and I use that factor form of the derivative. And so now at our level here, then we should be able to do this quickly, right? the equation here produces x equals 0. That's one solution. And the other solution would come out from minus 2x plus 3 equals 0. And minus 2x plus 3 equals 0 here is going to give me x equals a negative 3/2. See? Positive 3/2. Okay, so we found two critical values. And again, keep in mind at this point we have only found the critical values, meaning any one of these can be a maximum or a minimum or neither. Same way with this. This guy can be a maximum or a minimum or neither. So that's why we have to go with a sign chart. But so here's the problem. So now what's up with the interval? Our problem here, we found two critical values, and both of these critical values are in that interval. So we're going to use both of them. We're going to consider both of them. Okay? Now, it didn't happen here, but I'm saying what if, right? I'm saying that in case that, our solving would come out with x equals minus 10, for example, being another critical value. Remember, critical value came out by solving the equation. So sometimes, depending on how we solve the equation, we may run up into even a lot more than two critical values. And then, so when your problem comes with a given interval of restriction like that, then make sure to roll out those critical values that's not in the interval. Okay? And so if it has things like that, we have to rule that out. Okay? But of course, it really didn't happen in our problem right here. So I'm just going to disregard about that and erase that away. Okay? So I was just putting up a what if situation right there. So now we got the two critical values. Let's now do the sign chart. And then so between the two critical values, 3/2 is of course larger than 0, right? So now I'm going to draw, see, there's 0 here, there's a 3/2 there, right? And so once again, we have broken our interval, our line of numbers into three separate intervals. But now keep in mind again that we have a boundary anywhere from minus 7 to 7. See what I'm saying now? And so I'm putting with that completely with dotted lines simply to indicate for you guys that it's just something to be aware, and sometimes you don't even have to. Sometimes when you see me doing the work, I don't even have to put that down. It's just something to be aware of. And so now when you choose your test point, make sure you choose, see, in this interval, make sure you choose those values, yes, less than 0, but still being greater than 7, greater than minus 7. Okay, so that's something to be aware of. And then also pick a testing point here, right, so that it's greater than 3/2, but still less than 7. Because be aware that we're only working with anywhere inside of that interval from minus 7 to 7 here. Okay, and then I'm putting that here in dotted line, indicating that it's not required to put it there. It's just something for you to be aware about. So now let's go ahead and do the sign check. And so once again, this means x less than 0, x between, right, 3/2 and 0, and x is greater than 3/2. Okay, and so here let's speed up the process here. I could just choose one, and you guys are well familiar with that now. So I'm going to go with x equals -1, okay, as our test point. Okay. So now I'm going to quickly calculate the derivative at x equals 1, right? I mean at x equals -1. So that gives me, see, the factor form was -1 all squared times a -2 times a -1 plus 3. We good with that there? Okay. And so that here easily runs into a positive for that square, because any square is going to make it positive signs, right? That is a -2, that is a positive 2 plus 3. And so it's making it another positive. Okay. So my overall sign here of the derivative in this interval, and of course greater than -7, we're talking about positive sign. So our function here is increasing. So f prime has positive sign in that interval, meaning the function, right, is increasing. So we're still doing the usual work. We got to find all the local maximum and local minimum first. And then the next one right here, we can pick a x equals 1, okay, because it's between 0 and 3/2. The 3/2 is 1.5, right? So x equals 1 is sort of like the best candidate. F prime of 1, right? I'm going to do that again. 1 all squared times -2 times 1 plus 3. And this is now making it, that's positive. That factor after the square. This is also still positive because you see 1 times negative 2 is negative 2, right? And plus 3 is making it positive here. It's negative 2 plus 3, right, is positive. Positive sign right here. So our function is still increasing in that interval. Okay? And then here I can choose x equals 2, for example, right? That's our test point right here. And then we go f of 2, right, equals, now I got 2 square, now multiply with negative 2 times 2, right, plus 3. That's now positive for that square, but the work here in this big parentheses is going to be a negative this time. So our function, our derivative has negative sign in the interval anywhere, between 3/2 and 7. And so that's negative. So being negative means the function is decreasing, right? And so now we have, right on the line chart right here, and we're going to put it all together in one big conclusion. But see right here, similar to the earlier problems we've done, right? This is a local maximum. This critical value right here, see, the function was increasing, then continue increasing. So here it's a neither. Okay? It could be like a waterfall shape like that, right? It's rising up and continue and bend a little bit and continue rising up. All right, so we've found all of that. And we're going to kind of come to that ultimate final conclusion later on where we put down all of the values. So now, back to the function, right? Back to the problems here. Now, what's up with the absolute maximum and absolute minimum? Okay? The idea now is that, you see the word is saying it's the max, it's a height, it's the highest, but absolutely the highest, absolutely the highest. The idea now is that when you are having a function that can a lot of time, it swings up and down, right? Local maximum and local minimum, we can have multiple. For example, this guy here is local maximum. That guy here is also a local maximum. Okay? And then now, so think about it. Absolute maximum just means, among all maximums we can find, who's the absolutely highest? Okay? Who's the highest guy, right? Absolutely. And then we have multiple local minima, right? We have multiple local minimums right here. And so among all of the local minimums, absolute minimum is the one that's absolutely the lowest of all. Okay? But now in this philosophy right here, in this philosophy that I was saying, then the problem came with an interval of restriction. The problem that we have here, our function comes with an interval of restriction from -7 to 7. So think about it. Now, I didn't put that in my graph right here, but the idea is there's an interval. There's an interval of restriction. So we restrict our function from some value A to some value B right here. Okay? And so at A and B, we have the two endpoints. There's a left endpoint, the point on the graph that's corresponding to the left end of the interval, and the point on the graph that's corresponding to the right end. So there's a left endpoint and there's a right endpoint on the graph. And so now, when you're searching for absolute maximum and absolute minimum, make sure to also include the values of the two endpoints. Make sure to include the value of the two endpoints, because yes, even though among the local minimums right here, you may find someone who's the lowest, but you make sure you still are gonna compare with the endpoint, with both of the endpoints, because who knows, maybe one of the endpoint is still going lower than that point. Right? So I hope you guys got my the explanation. And then again, in terms of searching for the absolute maximum, yes, the major idea is to compare among all the heights, who's the highest. But it seems like we've spotted this guy, but who knows? Comparing that together with the endpoints, who knows? Some of the endpoints may go even higher. Okay, that's why in that way right here, make sure we include the values of the endpoints. All right. And so now at this point, here's how I'm organizing the work right here. I've given out that explanation. The idea is we're going to have to compare all heights and to recognize who's the highest guy to be absolute value. to be the absolute max, and then all lows right there, and who's the lowest one, that's the absolute minimum. And that means what? I'm going to have to calculate. Okay? And this guy here is a neither, so we don't have to worry about that. There's a value at the 3/2. This is our local maximum value, isn't it? Okay? Let's go ahead and do the calculation here. Minus 1/2 times 3/2 to the 4th, right? Plus 3/2 cubed. Okay? Go ahead and do the calculation right there. And if you could, right, put your answers in fractions right there. It's easier to compare that way.
I got like 27 over 32.
Okay, 27 over 32. It seems reasonable. So right now, of course, we know that this is the local maximum value, but I'm not labeling that yet, okay? Because we are still in the work of searching for the absolute maximum and the absolute minimum. That's why for now we're just calculating, how high does it hit and how low does it hit here at different special points, including the endpoints. This critical value is neither, so we don't have to worry about that, right? We already calculated the value at the local maximum here. So now we're going to look at the left endpoint. Okay, left endpoint. Right, sorry for my shorthand writing right here, but so left hand point means you're going to substitute the -7, the left end of our interval, into the function. So we're looking at -1/2 times -7 to the 4th power plus -7 cubed. Okay, go ahead and get me that calculated value, and maybe somebody else can also do this. So let's divide the responsibility right here. Time's running short for us. So we got a right endpoint. Right? The right endpoint is found by substituting the right end of our interval, our restriction interval, into the function. And we're looking at -1/2 times 7 to the 4th, right, plus 7 cubed right here. Right? So go ahead and get these values so somebody else can also try this, and then we're going to put in the results together.
-1543.
-1543. Okay? But then right endpoint, anyone who got the right endpoint, go ahead and say it out for me. -857.5. Is that what you said?
Yeah.
Okay. All right. So we got left end, we got right end, and we've got that local maximum right here. So now, see, does that give you now a sense about who's the absolutely highest one and who's absolutely the lowest one right there? So this one here is a local maximum, right? It was a local maximum, but now also I'm putting a check right here because among all of these final calculated y values, right, this guy is also the highest of all. Okay, so it was a local maximum, but now also known as the absolute maximum. All right, and that's the idea right there. And then among all three values right here, once again, this one here is the lowest, right? Even though it was not among the local maximum, the local minimum, but it's still the lowest out of all inside of this restricted interval. So this one here, we put a check here. This is we call it's the absolute minimum. Okay. All right. So now putting the conclusion all together right here. Right, so to make it more precise right here, I'm saying that as a conclusion, f of x, right, has a local maximum, right, at x equals 3/2, and then the value for that, the local maximum value, right, equals to the function value at 3/2, and we did the calculation and it came out being 27 over 32. Okay, so we got that. That was about the local maximum, and now we can also say that f of x, right, has the absolute max. Okay, because a lot of time when it comes to, there could also be, there could also be the multiple absolute max because the function may hit, twice right there, hit that height twice right here. But here we have only one, so I'm just saying it has the absolute max, right? That is found at x equals also 3/2 like that, right? And then, so the absolute maximum value equals another, simply 27/32, okay? And then this left end point produced the absolute minimum, so just now note that in here, right? So f of x has the absolute minimum at x equals -7, right? And then the absolute minimum value, right, came out. But so the absolute maximum, the absolute minimum here is -1,543. Okay, so we found, that's how we found our answers again. Okay, 3 answers that we found. All right, and I have one more example in my notes here, but it looks like we have to wait for the next lecture again. All right, good work, guys, and thanks for showing up, and I'll see you all tomorrow, and still on Zoom again. Okay.
Thank you.
All right, so let me now bring in example 5 here. So we're still looking at the maximum and minimum values. So in this example, we got a function given as f of x equals x to the 4th minus 2x cubed. And this time, we want to find all local maxima, local minima. And also, we want to find the absolute maximum and absolute minimum. Right, so spend some time writing it down, and we're going to tackle it. And if possible, you guys have that problem from example 4, putting that side by side with you guys, because the problem here is very similar along the way, but there's going to be some slightly different in the situation right here. So that's just a recommendation. You have your example 4 that we've done previously ready by your side right there, so that as I go along with this, I can keep referring back to it, some of that, so that you can see the difference right here. All right, so now let's get in. So we have a function. And again, see, the reason I was talking about example 4 is the problem here that we're doing is almost like example 4 that we've had in the earlier lecture right here. We got a function given, and we are asked to find all local maxima, all local minima, and as well as the absolute maximum and the absolute minimum. The only difference with example 4 we've done here is in example 4, we had a restriction interval. Like say back in example 4, we were spending all of our time working inside of the restricted interval from -7 to 7. And this problem right here, we completely bypassed the restriction interval, meaning we don't even have one. Okay, we just work with the entire function. And then throughout the entire function, let's recognize local maximum, local minimum, and possibly absolute maximum and absolute minimum. And that's the intention right there. So usually in these days, before I get into the example, usually in these days, this problem it's not normally given anymore, because it's a little challenging. But we still have some time, so I want to introduce that a little bit for you guys to learn it. Okay, so we got a function, and once again, there's no restriction. We look at the entire domain of the function, and let's find local maxima, local minima, absolute maximum, and absolute minimum. Okay, and so let's get into the usual routine here. So yes, the critical values is the first thing we need to find. And so here, but in order to find that, let's look at f prime. So f prime for our function here is going to be 4x cubed minus 6x squared. And so we've been seeing that the kind of work here that it's highly recommended that we should factor it out. So I can factor out the 2x squared right there, right? And making it now 2x minus 3 being in my factor. Okay, so the function was 4x cubed minus 6x squared. The function was x to the 4th minus 2x cubed, and then the derivative came down to this. And I decided for a good purpose later on, factor that out. Okay, and so in that way, and we're on our way to find the critical values. So now I'm looking at setting. I'm going to let f prime, right, of x to equal 0. And that leads to producing the equation 2x squared times 2x minus 3 equals 0. Okay. And like I said, these two are exactly the same, but I purposely used a factor format there, making it easier for solving the problem. All right. And so now from that way right here, we come up immediately with two answers, right? So x equals 0. That came out from this factor. And there's x equals 3/2. That came out from this factor. All right. So as far as the critical values, we've found the two critical values. Okay. These are critical values. So throughout the entire function, no interval of restriction this time. So we take all critical values. That's another detail I want to add on right there, because the problem here is so like example 4, okay? But in this case here, we don't have a restriction interval. And so every critical value that we found, we use it all. Okay, we're going to have to use it. All right, so now we're going to use a first derivative test to check for the, the increasing, decreasing, so that we can detect there being a minimum or maximum for each of the critical values. So now I'm going to go with the sign chart. So the sign chart is in the next step. So from the two critical values we've found, I'm going to put down the smaller one first, which is 0. And then there's a 3/2. Okay. And now upon putting down these two critical values, that we have broken down our line of numbers into 3 separate intervals, right? Just like usual. And so that's for x less than 0. That is for x between 0 and 3/2, right? And this is for interval here is for x greater than 3/2. Okay. And so we're going to do some checkpoints again. So here I can check with x equals -1, for example, right? We can check with something like that. And here I can suggest x equals 1. Okay? And you guys can pick your own checking test point as well, okay? Because we've done this quite a few times now up to this point. And then here I can go with x equals 2 as our checkpoint, because x equals 2 is greater than 3/2. Okay? So those are the checkpoints. And so for that checkpoint, x equals -1, our f prime here, right? In factor form again. The factor form is always the better one. So 2 times -1 squared, right? Times 2 times -1 minus 3, right? So it comes out for me, so that should come out for me being what? That's a positive, right? And then here is because square is a positive, and then that overall here is negative. So the sign here comes out, whatever that number is, but it's negative. All right, so I don't really need the final value, but I need the sign of our derivative. That's what matters. So in the first interval, I'm looking at being negative interval. Okay, see, because that 2 is a positive sign, right? That -1 all squared is a positive sign. Okay, and then that quantity in parentheses is here, gives me a negative. That's why I ended up with the final negative. Okay, and so in that way, so our f prime is known to be negative in that first interval. And so that means correspondingly the function is decreasing. From the left to the right, I'm drawing that pointing down arrow. Yes, and you can make note, it's decreasing. And then I'm doing that again with this test point in the middle interval right here, right? This test point x equals 1. And I should have put that as -1 here. And so f prime of 1, I'm substituting in that test point into our derivative. That gives me 2 times 1 squared times 2 times 1 minus 3. Right? That is a positive. That 2 factor is a positive. That 1 squared is also a positive. And 2 times 1 minus 3 is a negative still. Okay? So the overall product here turns out negative signs. So I have another negative sign right here in that interval. So our function further decreases, right? It's decreasing in that interval, in that middle interval. And then one last one. And with my narrow board space right here, I can squeeze that in. So when x equals 2, right? Substituting that into our function, into our derivative, we're looking at 2 times 2 squared times 2 times 2 minus 3, right? So this time it's surely positive, and that third parentheses also give a positive, so it's all positive, right? These are all positive, okay, multiply together. So in that way, my final outcome here is a positive sign. So now this interval gives me positive sign. That means the function now is increasing, right? From the left to the right, I draw that arrow rising up right there. Okay, so that's increasing. All right, so now we have detected that this critical point here is neither a maximum nor a minimum, right? That one is neither. But this point right here, right? What do you guys say? What would you say? Someone tell me. This x equals 3/2 here as a critical value. Should we decide that as a local maximum or local minimum?
Local minimum.
Local minimum, right? So here we got a local minimum. So as far as finding all the local maxima and all the local minima, we have found all of them, right? And again, that's similar argument I've been making. I should have stated that when I was still on the other board. But you see, the function was a polynomial. And after taking the derivative, it came out as another polynomial. So being a polynomial, there's no possibility about being undefined. That's why I didn't even mention about it anymore. So I've been saying that carefully over the past examples, but now when getting into this, then you guys are fluent enough, so I can assume that I don't have to, but just a reminder, right? Critical value is where the function is undefined, or the function, critical value is where the derivative of the function is undefined, or the derivative equals 0. But like I said, the derivative here is a polynomial, so there's no possibility for being undefined. That's the reason why I went directly into setting the derivative equals 0, because there can still be values causing our derivatives to equal 0. And these are the critical values that we found. Okay? And so in this way right here, I stated that simply because now really this chart has described all of our critical values. We found only 2 critical values. One of them is neither a maximum nor a minimum. This guy here is a local minimum. Okay? But the critical values only tells you about maximum and minimum. I mean local maximum, local minimum. So now, when we're looking at that, right? Unlike example 4 we have done earlier, this one here, there's no endpoints. So it's hard, it's going to get challenging to decide who's the absolute highest one and who's the absolute lowest one. Right there. Okay? And so now I'm going to have to say, first of all, let's just look at the local minimum right here. F of x, right, has a local minimum at x equals 3/2. So we stated that result. This is where we found the local minimum. And then the local minimum here, right, equals the function value at 3/2. So that gives me, what did that give me? So go ahead and do the calculation for me. Our function was x to the 4th minus 2x cubed. You guys had that written down on your notes, right? Yep, that was our function right here. So go ahead and substitute 3/2 into the function and get that calculated for me. Right here, negative 27 over 16. Right?
Negative 27 over 16.
Over 16. Okay, so negative 27 over 16 is our local minimum. But so that's not all of the problems, right? And this time we found by far no local maximum, right? So that's a couple of things to be aware of. See what I'm saying now? So now in the next step, after we have found all of the local maximum and local minimum right here, there's no local max for this problem, and there's one local minimum at this critical value, and it gave the value as low as negative 27 over 16. So here's one thing that I have to bring back from pre-calculus 1 right here for with you guys right here, and all of those details come back and really pay good result here. And I actually mentioned this throughout our earlier learning times before. But the function right here, f of x, right, x to the 4th minus 2x cubed right here. It's a polynomial, isn't it? Polynomial function, right? What degree is this? Somebody can tell me what degree this polynomial is.
4.
4, right? So it's degree 4. Okay? Even degree. It's a polynomial with even degree. What about the leading coefficient here? Is that a positive or negative leading coefficient? One more time?
Positive.
Yep. So we got a positive lead coefficient. Okay. You guys see where I'm going with this? That means the two endpoints, the two end behaviors, even though we never had a restriction interval, but the whole graph right here in full, the right end has to point up, and the left end also has to point up right here. And whatever in the middle, I'm not concerning right now. But the two end behaviors, so we discussed about this, right? Back in those days, we were doing limits as x to infinity or in limits as x to negative infinity. And so now I'm bringing back that result right here. The function has the two end behaviors both rising up. Okay, and so in this way, and again, there's no restriction interval. So in that way right here, can there be, because the way how the function is, the two ends have to infinitely rising and rising unlimited, right? So can there be an absolute maximum? Can there be an absolute maximum?
No, right?
That's right. There's not, right? Because see, absolute maximum means no matter how far the graph extends, there's just no one being higher than that absolute maximum if you recognize it. But in the way how it is, if you set a max like right here, it's still going to go surpass it, right? And if you set a higher max, it's going to still surpassing it because the two ends is going to keep rising up. You see what I'm saying now? And so as far as the absolute maximum, we found none right here based on that observation. So that it leads to, see, understanding the two end behavior right here, right? It leads to that. You guys with me on that so far? But so because of that argument right there, it leads further. What about the absolute minimum? What do you think? The absolute minimum will surprisingly turn out to be, see, all of those guys between, because the two end points, the two end side right here, the two end tails right here, will keep rising up, right? And so we don't have to worry about the maximum anymore. But the minimum is going to be somewhere in a middle part right here, right? So we have already reached down, the function already hit down to as low as negative 27 over 16 at x equals 3/2. You guys agree? So at that local minimum, now that local minimum here also becomes the absolute minimum. Are you understanding my explanation right there? And so now the absolute minimum, okay, happening at x equals 3/2, right? And the value right here, absolute minimum, equals to really as low as negative 27 over 16. So in this problem, we only had one local minimum, but in some other situation where you have already proven that there's no maximum, there's no absolute maximum, and you found multiple local minimum, then make sure you compare among those local minimums, and whoever the lowest of all the lows, that's going to be the absolute minimum. Am I making my point right there? So in here, since this is the only local minimum, so we have to make conclusion that it was a local minimum, and further it is now an absolute minimum, the absolute minimum of our function. It's happening at x equals 3/2. Okay, so that's the way how we utilize we have when we're finding absolute maximum and absolute minimum for a function that has completely no interval of restriction at all. Then we have to bring in the end details. I mean the end behavior details here, so that we can find out. Right.
Wait, so if this equation was like limited by an interval, like the last example, would the absolute max?
Yep.
Be
so
over
if it's limited like this, right?
Yeah.
If it has an interval of limited right here, then yes, you do bring in the endpoints, and you may want to compare that with your, see, there's going to be some local max and local min inside in between. You see what I'm saying there? Okay. And so we compare all of the local max, all of the local mins, right? And also compare with the endpoints to find out the absolute max and the absolute min. Okay?
All right.
So that's how we did that in example 4 as a generality. But here we don't have, in this problem here, we don't have the interval restriction. Okay, so whatever is swinging up and down in the middle over here, aside from the two ends, and I made my argument that the two ends here will keep rising. That's how it led to having no absolute maximum. And absolute minimum will come out from comparing all the lows that happening among these guys in the middle area right here. Okay, and by saying the middle, I didn't really mean like absolutely in the middle, but it's just like the central body part of the graph, right there, not the two ends. All right. You guys with me on that still? And then there could be time that your graph goes like this. See, completely pointing down on the two ends here. Then something like that, right? There's no absolute minimum in a graph like this. But then the absolute maximum can come out by comparing all of these local max right here. Are you guys following with the situation right there? Right, so in a graph like that, in that case right here, then there's no absolute minimum, but there's going to be the absolute maximum based on whatever being the highest peaks, right, among all of these peaks like that. And that's the idea of how we detect the local maxima, local minima, and together with the absolute maximum and absolute minimum. And so, as far as the basic fundamental of finding maximum, minimum value, you have learned it all here. But we will keep spending time looking at maximum and minimum value because we're going to learn even better methods. So far, the essential theme is to use the first derivative test right here, because to check for these local maximum, local minimum, we use the first derivative, and we put it in sign, charge, and all of that, right? And so that we can detect who's the local minimum, who's the local maximum, and who's neither, okay? And then from there, we found our local maximum, our local minima, and local maxima, and then along with that, we got the absolute maximum, absolute minimum. So we're still gonna look further for better, or I shouldn't even say better, some more options, some more methods to find local maximum and local minimum, okay?